Good morning. So today we're going to talk about how we establish the equations of line and planes using vectors. Today, after this section, there will be another section on some important 3D objects like quadrics, surfaces with certain properties. These will be our default examples for the figures we're going to need to use to illustrate the concepts, calculus 3 concepts we'll talk about later. So the elementary shapes, of course, are lines, planes, and then later on we're going to talk about quadrics, which are shapes like, some of you might know this already, like ellipsoids, paraboloids, spheres, and so on and so forth. Typically we're going to use spheres, paraboloids, ellipsoids, because these are kind of the easier ones to visualize, and we can quickly derive enough examples to learn the calculus 3 specific tools. Let's get into the subject of the matter here. One quick remark which I'm going to need once I'm going to go over the stuff for today. I don't know if I mentioned this. I think I mentioned it indirectly, but if you have two vectors, one of them and a scalar multiple of the other, of the first one, so one vector and a scalar multiple of the same vector, then V and CV are parallel. In fact, that is a quick way to check if two vectors are parallel. Because remember, the scalar only modifies the magnitude, not the direction. So for example, let's say I have a vector 1, minus 1, 3, and another vector minus 3, 3, and minus 9. I can quickly see that the second one here, if I pull the minus 3, the scalar minus 3, that's going to be 1, minus 1, and 3. So therefore, these are parallel. This is a direct consequence of this angle formula between them. If you do the cross product, it's going to be 0, sine of 0, 0, remember? And depending, yeah. So, well, I mean, depending on the orientation. So the angle could be 0 or 180 degrees, right? Because like in this case, for example, if 1, 1 minus 3 is over here, then the other guy is going to be 3 times as long, but in the opposite direction, right? Because it's minus 3 V, right? But the important thing for our purposes here, that's what I want to emphasize, the lines over which these vectors are located are parallel. So what this has to do with the equation of a line? Well, how do I identify a line in 3D? Now remember, in 2D, you just needed a point and a slope, right? So in 2D, I give a point, x naught, y naught, and I give a slope. But because you are in 2 dimensions, the slope basically can be just identified by the angle between, tangent of the angle between the line and the x-axis. That's why you have basically a number that identifies the direction of the line, right? So you have a slope, typically denoted by m. Again, that's going to be the tangent of that angle, and then a given point, and then from there you get your point slope form of the equation of a line, which I'm assuming everybody is familiar with this since you reached successfully the calculus 3 stage. Now, what is the equivalent in 3D? Well, you can still start with a point or 3 coordinates now, right? So the starting point on the line. But the direction cannot be given by a single number. Now remember, the lines can point in any directions all the way around the point in space. So you basically need a given vector, let's call it V of coordinates A, B, C, that indicates the direction of the line. Geometrically, this should give me enough information to derive the equation of that line. So let's just see how we derive that formula. It's very simple stuff, but in the beginning, again, if you're just in the beginning using vectors, go a little bit slower to visualize correctly everything. Okay, so let's sketch our coordinate system here. And let's say our point on the line is here, and suppose, let's use a different color, suppose my direction vector in the component form is over here. So that's the vector v of coordinates a, b, c. All right, so I need the equation of this line that goes through the point x naught, y naught, z naught, and is parallel to the vector v. Okay, so how do I do this this stuff? We're using vectors, obviously, and I want to point out that if you want the equation of the entire line, which is infinite, right, on both sides, if you want, of x naught, y naught, z naught, doesn't really matter where v bar points, right? I mean, we're just looking at basically the line where v bar is situated, right? That's the important stuff. So when you pick your vector that indicates the direction of the line, the actual way the arrow points, it's actually not critical. The important thing is that that line where the vector is situated. So how do I actually come up with the equation of the line? So let's look at the vector connecting, and let's call this vector connecting the origin to the given point on the line. Let's call it r naught. Again, I'm gonna remind you not to confuse the vector with the actual point. So by r naught bar, I'm talking about the vector with components x naught, y naught, z naught. So the vector that points, well, the vector that has as a terminal point the given point on the line. Sometimes this is also called the position vector of the point x naught, y naught. Position vector, as the name implies, means the vector that points to that point on the line. Since when you obtain the equation of any geometric figure, you want to have a description of a generic point on that figure. So you always pick a generic point, x naught, x, y, z. And the idea is to find a relationship between x, y, and z given these elements on the line, right? So given the point x naught, y naught, z naught, and given the direction of the line. So keep in mind these are the given elements, as you will see with example in a minute. All right, so let's denote by r bar the vector that points to this generic point. So let's denote by r bar the vector with components x, y, z. So using vectors, what is a way to describe that point? Well, we're going to actually make use of that triangle that I just formed here. So let's see if I can do this with a different color. Let's use blue. And let's see. Minus r naught. I want to make it. Yeah, let's make a vector from r naught to r, like a vector on this side of the triangle. Let's see if I can make it visible like that, pointing from x naught, y naught, z naught to x, y, z. Okay, cool. All right, so remember now the addition of vectors, or the vector addition. Yeah, I mean one of the other elementary operations we talked about. And if you look carefully, in fact, the blue vector added to r naught will give you r, right? So I mean, let's actually make a notation for this blue vector. Let's call it, well, actually, I'm not going to give it any name. Just look at the figure carefully here and notice that r is the sum of r naught and the blue vector. I don't want to introduce extra notations that I won't use for more than a second. So the blue vector, which actually describes, if you think about it, the relationship between x, y, and z, is going to be the difference, right, between r and r naught. Okay, so this is just vector addition, just coming from the vector addition. But on the other hand, the blue vector is also parallel to the direction of the line given in the problem, ABC. So how do I write that based on the remark I just mentioned in the beginning of the class here? Two vectors are parallel if one is a scalar multiple of the other. So I can state this in a very compact way in the following shape. R minus R naught parallel to blue vector, parallel to, to V naught, which is equivalent to R minus R naught being some scalar multiple T with V bar. So T is a scalar. I typically denote it by T in this context because this basically leads to, you'll see later, to parametric equations, and typically T is a traditional notation for a parameter in parametric equations. But let's encapsulate this in a formula. This is basically the vector form of the equation of a line parallel to V and then through a point x naught, y naught, z naught, which of course is identified by the position vector x naught, y naught, z naught. All right, so that vector form of the equation of the line will be r minus r naught equals t v bar. R bar minus r naught bar. Okay, so where t is a parameter that takes any real number. Right, for each parameter t, you're going to end up with a point on the equation of that line. So let's go over an example, and we're going to get through. Well, let's actually write down the parametric form, which is more useful, and you'll see it more often in computation, and then we're going to get to examples in a minute. So let's stay tuned for the second page. All right, so I wrote here again the vector form of the equation of a line. There are other forms which again are more useful in different contexts. So all of them are obviously equivalent to each other. So in this case, if I write this equation by components, then so r bar is x, y, z, x naught, y naught, z naught, and then t, a, b, c. Now if I move this to the right hand side and combine everything on the right hand side with the vector. So first of all, perform the scalar multiplication. That's going to be a t, b, t, c, t, added to x naught, z naught, y naught. You're going to end up with this equality. This is what you will see more often in various examples. These are the so-called parametric equations. Of a line. So this is just simply stating the equalities component by component. X equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. Whenever you see an equation like this, it's very important to remember the components, the meaning of the components, right? So x naught, y naught, z naught is on the line, a point on the line. It's a point on the line. It's kind of messy here. So is a point on the line. And even more important, remember where these coefficients of t come from, meaning that those coefficients together in a vector form the direction of the line. So whenever you need quickly to come up with a vector parallel to that line, remember that vector comes from the coefficients of the parameter t. And then you may see another form which is also used sometimes. This is essentially solving for t in each equation and set equal to each other each expression that results from these equalities. This gives you what is called the symmetric form of the equation of a line. So, for example, from the first equality, t is going to be x minus x naught over a. Then from the second one, t is y minus y naught over b, and then z minus z naught over c. Right, so three forms, you can write them on the formula sheet and then use them however you like. Of course, I mean, if the problem doesn't specify how you should use, which form you should use, you pick the one that you like. And let's go over a couple of examples. Again, I strongly encourage you to actually pause the video, work ahead of me a little bit, see if you can get these examples on your own, and then check the computation with me. There are no specific, there are various ways you can do the same problem, so you should probably try to do that just for practice. So let's start with the basic one. So suppose that, well, one important remark that I want to make here, actually, which is quite important here, the parametric equations are not unique. Notice that depending on the choice of the point you pick and the direction vector, you could have various forms, right? So for instance, let me give you an example here. X equals 1 plus 6t, y equals t, z equals minus 2 plus 2t is going to be the same line as x equals 1 plus 12t, y equals 2t, z equals minus 2 plus 4t. It emphasizes the same initial point. So the initial point on the line that you used is 1, 0, minus 2. But the direction vector, in the first case, the direction vector is 6, 1, and 2, right? The coefficients of t. And the direction vector in the second case is 12, 2, and 4. But obviously, it's a scalar multiple of the first one, so it doesn't matter. The difference is that, of course, for the same point, you get different parameters. So for example, if t equals 1, if you plug in t equals 1, you get the 0.710. But the same point is obtained if you use the second version of the equation for t equals 1 over 2. So same point, different parameter values. Parameterization, again, are not unique. This is not a bad thing, actually, because you'll see later in many problems or applications, it's a good thing that we have the freedom of choosing various parameterizations. So some of them are easier to work than the others. And sometimes it can be confusing because if you use a different initial point, again, it's gonna look weird. By the way, for this example, if I want symmetric form, you just solve for t. Just keep in mind that in this case, of course, the direction of the line is read at denominators, right? 6, 1, 2. Always remember the meaning of the parameters. I mean, of the elements in an equation, in a formula. So let's continue with another example. Let's say I want to find the equation of the line through the points, another example here, through the points a of coordinates minus 1, 2, and 1, and b of coordinates 0, 1, and 3. So again, the beauty of the whole thing is that we don't have to sketch the picture at scale here. I mean, if I can apply the formula immediately, don't sketch anything unless you need to. So I'm going to write that maybe later as a general remark, because that's the power of these tools, right? I mean, you need to visualize a little bit, but we only sketch just as much and only as needed. Here I don't need to sketch anything at scale. I'm just going to put here a line just to have an idea. So I already have a point. What do I need, right? I need a point and a vector parallel to that line in order to apply the equation of the line. I can choose any point I like. So for example, I'm gonna choose -1, 2, 1 as the starting point. How do I obtain a vector in the direction of the line? Well, either from A to B or B to A. That's the easiest thing, right? So just choose one of the two vectors, from A to B or from B to A. Remember though that you need V in component form, because that's how you build the equation, right? So I need AB to be my vector V in component form, and since I started, I put A as the initial point of the vector. To make it in the component form, I need to subtract it from the terminal point B. 0 minus -1, 1 minus 2, 3 minus 1. So in component form, -2, -1, and 2. Perfectly fine is to choose BA. If you wanted to choose BA, of course, it's going to be 2, 1, -2. Either way is fine. -1, 2, 1, 0, 1, 3. Excuse me. Sorry. I made a little. Here, this is gonna be. I confuse myself with this parenthesis. This is just 1. 0 minus -1, 1. 1 minus 1 and 2. Good. All right, so this is ABC in the formula. And let's write down the parametric equations of the line. So x is going to be x naught, which is going to be -1 in this case, plus AT. Y is going to be y naught, which is 2, minus t, and z equals 1 plus 2t. All right, so symmetric forms, let's write those guys as well. So x plus 1 over 1 equals y minus 2 over -1 equals z minus 1 over 2. Notice that you prefer to leave the minus on the bottom here. So in other words, just keep the numerators as x plus or minus something, because only in those cases the denominators will indicate the correct direction of the line. So let's see. Maybe, yeah, so let's move on the second page with 1 or 2 more examples including lines, and then we'll get to the second part of today's lesson, which is equation of planes. All right, so we're gonna have our little sketch here in the three-dimensional system, but let's discuss for a moment how do we actually identify a plane in space, or geometrically speaking. What I mean to say is, how do I identify a plane? Notice that from basic geometry, there are multiple ways to define a figure, right? A fundamental figure like a line or a plane. For example, a line, you can define it as, you can identify it. That's what I want to mean, right? How do you identify it? You can identify it via 2 points on the line. You can identify it by a point and a slope or a direction, which is what we used in the previous part of the lesson. With the planes, we have actually various ways to do that. So first of all, via points only, you can identify a plane via 3 distinct points, right? So whenever you pick 3 distinct points, you're going to identify the plane. There's only one plane that goes through those points. That's why, incidentally, there is no way for a 3-legged stool to actually tilt, to wobble. A 4-legged one can wobble because if the legs are not level anymore, the 4 legs identify 2 different planes because they're not level anymore, all of them, right? So you pick 3 of them, it identifies a plane, and then other 3, another combination of 3, you have a different plane, so therefore it wobbles, it switches between one plane and another. But if it's 3-legged, might be crooked, might be tilted, but there is not going to wobble. So 3 distinct points identify a plane, but there are other combinations. You could identify a plane via, for instance, a point and a line. But notice these are equivalent, right? So I mean, equivalent to 3 distinct points. Now, for our purposes, because these planes are oriented in any possible shape, right, position in space, the most efficient way to identify a plane is actually via a point. Let's say you have a tilted plane like that. A point, x naught, y naught, z naught, and a vector perpendicular to the plane called a normal. So a normal vector is any vector perpendicular to the plane. So this is where the limitation of this method of teaching comes into play, because normally I'll see later on, I'm gonna add some little videos. I actually do a little bit of demonstration, right? So I mean, but you could do that on your own, right? You just pick, for instance, a piece of paper or something more rigid like a cardboard, and pick a point on it, and use, let's say, a pencil to indicate the normal, and then realize that if you keep the point there and then you change the direction of the normal, you pretty much can rotate the plane in any possible position, right? So that means, in other words, that is all you need to identify the plane. Some point on it and the normal, a specific vector which indicates the perpendicular direction over the plane. And at this point, notice I'm not going to make any reference whether you talk about a normal pointing on one side of the plane or the other side. We're not going to distinguish between the two. It doesn't really matter. It's still a normal, whether you take this one or its opposite, right? It's still a vector perpendicular to the plane. Later on, we will talk about orientation when the time comes. All right, so let's kind of visualize this with position vectors like we did it before. So suppose that my given vector is, excuse me, so the point given, it's over here. And then like before, let's call by r naught the position vector to that point. And let's see, let's say the normal, let me see how I do that. Let's say the normal to the plane points like that. I'm gonna use maybe a different color. Let's use blue. Suppose this is a normal vector over here. Okay, so the normal vector, let's say, has components a, b, c. And let's say we have another point on the plane which I want to describe via the equation of the plane. Over here, let's say x, y, z. And by r, we're going to denote the position vector to that generic point. Just like before, just like in the previous example. So roughly speaking, just visualize the plane over here, right? So we're trying to find the equation of, try not to make a mess here, but I hope you got the idea, right? So the plane that goes to the given point x naught, y naught, z naught, and a generic point x, y, z. All right, so now how do you actually characterize this generic point x, y, z with the given point x naught, y naught, z naught? Well, notice that if I connect the two, these 2 points, the given point on the plane, and in fact, let's use a different color still. I connect these 2 points. The 2 lines are perpendicular. So in fact, let's write this in words, right? So the line that connects any point on the plane with a given point on the plane, x naught, y naught, z naught, is perpendicular to the normal. That's why, that's the meaning of the normal, right? It's a vector perpendicular to the entire plane. So at this point, it's just a matter of stating this with vectors, right? Let's make a vector out of these 2 points. Right, so the vector from x naught, y naught, z naught. And notice that that vector in component form, the way I wrote it, again, it's a difference between r and r naught. Right, so the red vector plus the r naught is going to be r. Right, I form again a triangle there. So the red vector, by the way, is going to be the difference between r minus r naught. And then I'm going to state now the fact that this has to be perpendicular to the normal m. Right? There's a 90 degrees angle over here. Remember one of the applications of these vector operations that we talked about before? How do we actually write that 2 vectors are perpendicular? Like, what's the easiest way to do this with the vector operations? So hopefully you remember that the dot product being 0 is the fastest way to state that 2 vectors are perpendicular. All in all, this basically encapsulates the so-called vector form of the equation of a plane. Now, actually, let's stick to the red color. By the same token, we can quickly write this in terms of components. So the normal, I denoted by ABC. By components, r minus r naught is x minus x naught, y minus y naught, z minus z naught. So if we perform the dot product, we end up with a times x minus x naught, b, y minus y naught, c, z minus z naught equals 0. This is the form that we're going to use most often. The equation basically that goes to plane, right? Plane through x naught, y naught, z naught with normal ABC. So the coefficients of these parentheses of x and y and z will be the normal. For convenience, we often write So this is, by the way, this is called the scalar equation of a plane. Probably because it comes from the scalar, well, actually I don't know why it's called scalar. I think that's the name given. And immediately related to this, if we expand these parentheses and move all the, so expand the parentheses and just keep ax, by, c, z on the left, you get to the format which is more compact, and that's used more often, which is again related to this, and that's going to be ax plus by plus cz equals some number d. Now the advantage of this is more compact. This is the linear equation of a plane. But the disadvantage is that you cannot see quickly the starting point that you use on the plane. But you know, if you want to give the equation, the last answer as the equation of a plane, typically we leave it in the linear form, this last one, because it is more compact. And let's actually do a quick example, followed by some other examples before we call it a day. So let's say I want the line through the point 1, minus 1, and 1 that is parallel to no, excuse me, I was looking at a different example. I want the equation of a plane through the point 2, 0, 1 perpendicular to the line given by the parametric equations x equals 3t, y equals 2 minus t, z equals 3 plus 4t. All right, so notice that in this case, the point is given, 2, 0, 1, the line is given, right? Given by this, these parametric equations. And I want the line to be perpendicular to the plane, right? To the plane that goes to the point 2, 0, 1. So what could be the normal to the plane? Well, the normal is going to be the vector parallel to the line. Right? Any vector on that line can be used as the normal. What's the quick way to extract the parallel vector to the line? I'm looking at the coefficients of t in the parametric equations. Those are 3, minus 1, and 4. So I can use that as the normal to the equation of the plane. So then the equation of the plane is going to be 3 times x minus 2 plus negative 1 y minus 0 plus 4 z minus 1 equals 0. If you expand this a little bit, that's going to be 3x minus y plus 4z, and move the other constants to the right. Minus 6 becomes plus 6, 0 plus 4 equals 10. So 3x minus y plus 4z equals 10. So let's stay tuned for other examples. All right, so as another example, let's say we want the plane through the points, the equation of a plane through the points p of coordinates 0, 1, 1, q of coordinates 1, 0, 1, and r of coordinates 1, 1, 0. Remember not to confuse the points with the actual vectors, right? So here I'm giving you 3 points. They determine a plane. You can use either of the points as initial point on the equation of a plane. You should maybe repeat the exercise and use one of the other two just to see if you get the correct or the same answer as mine. So how do I get the normal to the plane? Well, the normal, remember, perpendicular to a plane, you may think about producing a cross product. You pick 2 vectors in the plane, so cross product of 2 vectors in the plane. That's the default way of getting basically normal vector to the plane. But you don't have the vectors yet. Remember, I mean, I notice often these mistakes. People do the cross product involving these coordinates. These are not vectors, these are points. You need to come up with two vectors. And you have lots of choices, right? You could write, for example, QP, QR. It doesn't matter, as long as you pick two distinct vectors coming from these 3 points, they are as good as any. But you need to write them in component form, so you have to be careful here, right? So if I say PQ, that means P is the initial point. I need to subtract P from Q, and that means the actual vector PQ in component form will be 1 minus 1, 0. Similarly, I need to subtract P from R to put it in the component form, and that'll be 1, 0, negative 1. And now my normal is the cross product between the two. And so that's going to be minus 1 times minus 1 minus 0, which is 1. Middle guy is minus 1 with the opposite sign, that's 1 again. And then 1 again, the last component. So it should be 1, 1, 1, depending on the order of. So basically 1, 1, 1 or negative 1, negative 1, negative 1, depending on the, or any multiple of this, depending on the way you chose this pair of vectors. So that's all we need, right? I mean, now let's say we're using P and the normal vector 1, 1, 1, using the scalar equation of a plane x minus 0, 1 times x minus 0 plus 1 times y minus 1 plus 1 times z minus 1 equals 0, which simplifies to x plus y plus z equals equals 2. Minus 1 to the other side, plus 2. Okay, actually, let's do even one more example, and I need to say something about the angle between two planes, yet another applications for that. How do I find the equation of a plane through the point minus 1, 1, 2, parallel to the point to the plane z equals x plus y. So here the schematic is you have somewhere a point minus 1, 1, 2. You have a given plane. Let's say this is the given plane. And I need the plane parallel to the given one. Once again, the actual given point to begin with is, I mean, the point to begin with is given, minus 1, 1, 2. We need the normal. Okay, how do we relate the normal with the given plane? Again, let's pause for a moment because this, I mean, let's slow down for a moment because again, this emphasizes the meaning of these formulas. Well, notice that the two planes have the same normal. Since the given plane is parallel to the plane I want, the normal to the given plane can be used as the normal to the plane I want. How do I extract the normal from the given plane? Well, I remember that if my given plane equation is written like this, if it's written like this, then the coefficients of x, y, z constitute the normal. Then I'm going to take the equation of the given plane, write it in this form, and then I can conclude immediately that the normal to that plane is 1, 1, minus 1. I hope you guys appreciate how efficient these techniques are, because once you know the meaning of the formula, you can quickly obtain these important quantities just by reading the important information from the equation at hand. Okay, so 1, 1, minus 1 is the normal that I can use. And now the problem is simple, right? Using the point given in the problem and the normal that I just produced, then we can write the equation of the plane I want, right? So it's going to be coefficients of the normal 1 times x minus negative 1 plus 1 times y minus 1 minus 1 times z minus 2 equals 0. Let's simplify this a little bit. And then finally that gives me x plus y minus z equals x plus 1 minus 1, 1, 2. One minus 1 minus 2, yeah, because these two cancels. All right. Okay, so last topic, we're going to move on to the last page, the angle between the two planes, and that's it for today. All right, so in some problems, you may need to figure out a way to measure how far apart are two non-parallel planes like that. In other words, to measure something that we're going to define pretty soon, to measure the angle between two planes. So for example, the planes made by two axes any two planes made of the planes involved in the coordinate system, obviously they form a 90 degrees angle, right? So I mean, intuitively I can tell that, for example, the plane made by YZ and the plane made by XY axis, they form a 90 degrees angle. But how do we define it in general, the angle between the two planes? So as a definition, the angle between two planes is the acute angle, that is to say less than or equal to 90 degrees, the acute angle of their normals. So you define the angle between the planes via their normals. The reason why I choose the acute angle is for a consistency. Why we choose this acute angle is for consistency of the definition, because so you can have a single quantity, because then depending on how you compute it, you will see you either get one angle or its supplement, right? So in order to make a consistent choice, we always choose the acute angle. So if we don't end up with the acute angle, we simply write down the supplement of it. Now, I mean, this is just a small convention. It's nothing, hopefully nothing too confusing. It's just basically as a way to have a precise quantity of this notion, the angle between the two planes. So we already have the tools at our disposal to figure out how to approach this. So let's do right away an example. So let's say we have a plane of the equation 4x minus 2y plus 6z equals 7, and another plane of equation y minus 6z equals 1. Okay, so at this point, hopefully we could do this faster. How do we extract the normals? Well, they are written in the proper form, ax plus by plus cz. When I say proper form, I mean the form, linear form, in which the coefficients x, y, z are on the left and everything else on the right hand side. So you must write it in that form if it's not written that way already, so we can extract the normal to the planes. Normal of the first plane, coefficients of x, y, z, 4, minus 2, and 6. Normal to the second plane, there's no x, so that's 0, 1, and minus 6. Okay, so how do I find the angle between them? Any angle formula. So let's say I'm going to use the cosine formula for the angles between them, which involves the dot product over the product of magnitudes of these normals. So on the top I have 4 times 0 minus 2 times 1 plus 6 times minus 6. Magnitude of f1 and 1, 16 plus 4 plus 36. 0 plus 1 plus 36. So I'll get minus 38 on the top over root 56 times root 37. Obviously use a calculator, take an inverse cosine of that quantity, and you should end up with approximately 147 degrees. So you see, because there is no specific way to choose the normal. See, the thing is, there's no quick way to figure out whether we choose the normal on the acute side, oriented to the acute side, look at the top here on the page, or this supplementary angle side. There's no way to figure out quickly which way is which. In this case, we ended up actually getting the supplement of the acute angle, but that's not the problem. Then if I want to, again, provide the actual acute angle between the planes, I'll just basically provide a supplement of what I got here. So by the definition that we had here, the actual angle between the two planes is 33 degrees. If you chose the normals differently, then you would have gotten 33 degrees from the onset. Okay, so with that, that's it for today. I'll see you next time.